Welcome to Nameless Light, a podcast about science, politics, and arts. My guest today is Dr. Nathan Wiebe. He is a researcher in the field of quantum machine learning, and we sit down to talk about Microsoft's Majorana chip and its implications for the future of quantum computing. We had a great discussion, and I cannot wait to share it with you. I think let's start simple. So what is quantum computing and how is it different from classical computing?
That, Mike, is an excellent question because I think this is something actually a lot of people don't think about in a very clear way. And the truth of the matter is, at some level, we still actually don't fully know what the differences are between quantum and classical computing. At a foundational level, really, there's a deep question, actually, about what the main characteristics that separate quantum theories from classical theories. And the exact same thing ends up moving over to quantum computing. So it's a very complicated question about what the differences are at a fundamental level, but let me give you my best attempt at this. So what I would say is that the closest analog that we end up having to a quantum computer would be like a probabilistic computer. So, imagine an ordinary algorithm that you have that makes randomized choices. So it flips a coin and decides, hey, if it's heads, I'll move this way. If it's tails, I move that way. Now, when you have an ordinary probabilistic algorithm, it can go through a whole bunch of different branches by these coin flippings. And the probabilities that you end up getting measuring some particular outcome will be the sum of getting the probabilities of getting that algorithm from every path that it could randomly take through the entire computation. And so that's how a classical randomized algorithm ends up working. Now, in order to understand how a quantum algorithm ends up working, it's useful to think about what the difference between a quantum distribution is and a probability distribution is. So a quantum distribution, there's different ways of interpreting it, and I apologize for the experts who are listening. This is like a gross oversimplification. But at a high level, the difference between a quantum distribution and an ordinary probability distribution is a quantum distribution has the property that the sums of the squares of the elements add up to 1. For an ordinary probability distribution, it's that the sum adds up to 1.
I see.
Believe it or not, the entire power of quantum computing, in effect, comes from that one small little difference. And so shockingly, we found examples of cases where this difference between it being the sum of squares and the ordinary sum leads to exponential separations in the power of these two types of computers. And why, you might ask? Well, I'm glad you asked my rhetorical question. But the reason why is because if it's a sum of squares, you can have negative probability amplitudes. You can have complex probability amplitudes. And okay, so what? What's the big deal about this? Well, I said that for this randomized algorithm, if you were to carry it out ordinarily, the probability is going to be the sum of the probabilities through all the paths that you could compute. In the quantum case, now it's going to be the sum of all the quantum probabilities, which now can be positive or negative. So before, you had all of the possibilities adding together. Now, on a quantum computer, you can have possibilities interfere with each other. So this is kind of like, having a situation where you get up in the morning and, you could end up having pancakes or you could have cereal. Ordinarily, the probability of you having, breakfast would be the sum of the probability of you getting the two. But in quantum land, you could have those two possibilities interfere with each other, even if you haven't chosen either one of them yet. And this ability to have the different potential outcomes of an algorithm interfere with each other is entirely what gives us our advantage on quantum computers. And we can effectively get a whole range of different possibilities, exponentially many, to kind of talk with each other and collaborate in order to be able to solve problems through wave interference between these possibilities. Now, if this sounds complicated and hard to engineer, well, it is. And one of the big challenges with quantum computing for a very long time is that in order for us to be able to design an algorithm that uses a profitable way of these interference between the different possibilities to solve a problem, it kind of would require us to understand a system that's too hard for us to simulate on our ordinary computers as is.
Mm-hmm.
So it was very difficult for us to be able to design algorithms. And in recent years, due to a couple of breakthroughs that have come up, and I mean like really since about 2016, going through about now, we've actually just begun to build the first paradigms that allow us to systematically build quantum algorithms for given tasks.
Mm-hmm.
And this really has changed the way that we think about solving problems on quantum computers.
Mm-hmm. Great. And speaking of breakthroughs, let's talk about Microsoft Majorana chip.
Sure.
And yeah, it's sad that we only have 1 hour because I had a lot of questions about like all the areas of like quantum technologies, not just quantum computing. But I think even if we cover like this new chip for like 1 hour, it'll be an amazing show, and we'll learn a lot. So as we all know, Microsoft recently introduced this Majorana 1 quantum chip. Can you give us a high-level overview of what makes this chip so significant?
Okay. So this is something that actually, has kind of like a bit of a special place in my life, even though I haven't done any direct research on this. I spent 6-ish years working for Microsoft as part of their quantum effort. And part of it was actually taking a look at aspects of their individual chips. And the thing is that their effort to try to do this actually started in the early days of quantum computing. So to put this in perspective, what's the big challenge for quantum computers right now? The big challenge really is that their quantum information is incredibly powerful, but unfortunately, it's also like incredibly sensitive. Because just looking at a quantum distribution wrong is enough to damage the information that's stored there. And the environment, if you think about it, like everything around it, the circuits that you're building, even gas molecules colliding into your device, all of those things are kind of like the environment looking at your quantum state. And over time, it damages it. And this means that actually the very thing that we're using as a source of our power, unfortunately, is also kind of its greatest weakness. And the problem, effectively, is that due to all of this, our best quantum chips that we have right now have errors that are on the order of about 0.5% or smaller. To put this in perspective, the error rates that you end up having, in your cell phone or your laptop, are on the order of about 10 to the minus 13%. For just the raw transistors. It gets a little bit worse under some circumstances, but basically errors do not happen. But on a quantum computer, at least the current ones we can build, they happen all the time. So basically, the main goal is to find some way of storing our information in kind of a magic box. And this magic box has to have the property that nature can never measure the information that we're storing inside of it. And yet, somehow, we know a secret to being able to extract the way of this information that nature can't figure out. Because we need to manipulate it. We need to measure it, but we need to make sure that random noise can't. And this was the whole idea behind Microsoft's approach to it. It uses this idea called topological quantum computing. And the basic idea is that what you want to do with it is you want to be able to store your information in what are thought of as topological properties of a state. So let's put it this way, right? An analogy that I often like, and this is somewhat of an imperfect analogy here. An analogy that I like is, imagine you had a situation where you had a basketball versus a donut. Okay? We could basically imagine a situation where we could store information by saying, if it's a basketball, that corresponds to 0. If it's a donut, it's a 1. The big difference between a basketball and a donut is they're actually fundamentally different shapes. The reason why is a donut has a hole in the middle. The basketball doesn't. Now, you could consider, like, if they were made out of Play-Doh, right? And you could, push them around and bend them in crazy ways. You'd have to do a massive, massive change in order to be able to remove the hole or be able to create one. In fact, there's no way you can do what's known as a local deformation of the object in order to be able to do this. Now, if we considered having this in the real world, if the noise that we're looking at acting on, say, our sphere versus our donut was all local, it would be incredibly unlikely that jittering it around would fundamentally change the presence or absence of a hole for it, meaning that this topological information, i.e., the presence or absence of the hole, is incredibly robust to local errors. So the idea basically is, could we build a quantum states that have a really similar property, where the information isn't stored in local pieces of information, but rather in a global property of the quantum state itself? And then the idea is that, if you have random stuff in the environment that can only see local properties, not the global properties, they're not learning anything essential about the state. I.e., they're not learning the essential information, which is only stored in the presence or absence of a hole. And this fact that this global structure is kind of robust to local errors ends up allowing you, in principle, to be able to store information in a way that would be resilient to all of these errors in the environment. So the hope would be, the grand hope with topological quantum computing is to be able to reduce these error rates that you end up seeing of about like 0.5%, maybe to some numbers that are down towards like 10 to the minus 6 to 10 to the minus 10. Something like that is really kind of the grand hope. And if achieved, that could radically change our prospects for what we envision a quantum computer will look like in the near term.
I see. So, I have no background in physics, so correct me if I'm wrong. Are you saying that like the whole advantage here is that we get to store the information on like a surface or something, so that we can actually refer to it later? Because like with the, I guess, mainstream quantum technologies, the problem is that, as you said, like once you shine a light to see the state of the qubit, that generates error, and this is like a workaround for that.
Yeah, basically what I'm saying here is that the idea is that we're not storing this in the raw bits of information that we would end up seeing. Like, for example, we're not storing it in the positions of each of an individual electron. Rather, we're storing it in more global notions. We're storing it kind of in the correlations between them. And so what this ends up meaning is that if you had noise that's affecting not the correlations between them, but just like their individual positions, then those noises won't end up affecting the system.
I see.
So that's how that ends up working. Now, there's a question about how you end up building this in practice. At some level, actually, kind of the most popular approaches to this, done by Microsoft and Google, are actually mathematically kind of doing the same thing, believe it or not. So Microsoft's approach is to physically build new particles that have never been seen in nature that actually have this property. So the idea is that they want to be able to build systems that are capable of having what are called Majorana fermions in them. Ideally, they'd like actually another family of what are called anyons, which are neither bosons or fermions. They're things that have arbitrary exchange statistics between the two. And the idea basically behind it at a high level is that if you have these exotic particles, if we exchange them, then what we end up getting in this exchange process is we get different gates that are applied to this global information that's stored in the correlations between the two halves of this particle that we're kind of braiding around each other. And through doing these exchanges, what we can do is we can carry out quantum gates in a very, very protected fashion, because the exchange is changing this global information. It doesn't care about the local information. And so the noise that we would see otherwise kind of is irrelevant. The real big challenge, as I said before, is that this involves people building artificial particles that have, to our knowledge, never been seen before in nature. In fact, the way that they end up doing this is they use nanowires that are actually fabricated artificially, that are on the order of just a couple of nanometers across, and basically are put in an incredibly strong magnetic field on the order of a couple of Teslas, which is absurd, by the way. Like, that's the kind of field that you need to levitate a frog. And these wires are put in proximity to a superconductor. It turns out then that the superconducting particles can tunnel across, and if everything is set properly, the effective excitations of the system that you end up seeing, according to quantum mechanics, ends up giving you, or should give you, these particles that you end up seeing as their fundamental excitation. So it's nothing like like an electron, which is a fundamental real particle that you can see just about anywhere. These are effective particles that are being engineered inside these complicated systems. And I want to emphasize the complexity of this challenge. These are incredibly strong fields that have to be aligned very precisely with these nanowires, which are built out of exotic materials that have to be manipulated and read under extremely sensitive conditions and using fabrication technologies that are beyond state-of-the-art. The engineering task of getting any signal out of these experiments is monumental. So Microsoft has been trying to do this since about 2006. And, a couple of false starts have happened along the way, unfortunately. But there's a good chance that this might be the first example of this. A major challenge is that at present, there's other hypotheses that could explain the behavior of this. Well, they've built a qubit with it. They don't know if it's actually yet, for sure, one of these topologically protected qubits. So it might not actually have the protection. And furthermore, the noise is actually pretty high right now. So it's nothing like on the order of our best quantum bits that a company like Google or IBM can end up building at the moment. But the point is, it's the pathway forward. And there's a very real chance that Microsoft could actually, this could be, if Microsoft is right and everything ends up working out well, this could be a first step towards vindicating Microsoft's strategy. But let me turn and take a look at Google's strategy, on the other hand. Google is taking a look at a different approach. What they're doing is they are, again, taking inspiration from this exact same idea. And they're saying, okay, well, let's also try to store all of our information in topological structures inside quantum states. But rather than us trying to build particles that fundamentally, at a physical level, have this property, let's simulate them inside a ordinary quantum system that doesn't have these properties. And this uses technology that we call quantum error correction. And in particular, it uses technology known as the surface code. If you take a look at it mathematically, actually, the surface code is identical to the type of qubits that Microsoft is trying to build. So you can see, actually, these two things are kind of, at a mathematical level, the same thing. It's just what Microsoft is trying to do in hardware, Google is trying to do in software. So there's pros and cons. If Microsoft ends up sticking the landing, they could have hardware that is fundamentally, vastly better than anything that we're dreaming about right now. Google, on the other hand, the engineering challenges to building it are far lower, or at least I suspect they're far lower. But on the other hand, the overheads that we're going to need in order to simulate this, because we'll have to do it all in software, could potentially be a lot higher. So at the moment, we're not really sure which of the two approaches is ultimately going to be successful. But it's interesting that actually at some level, they're precisely the same strategy. It's just what has happened before this Microsoft announcement is we weren't positive that Microsoft's strategy would end up having a good roadmap forward to competing with Google. Google's approach seemed to be working out fine. They showed demonstrations that they can implement small versions of these quantum error correcting codes. But Microsoft's stuff was uncertain. Now it's making some people reevaluate how much, or if at all, Google is ultimately going to be ahead of Microsoft.
Mm-hmm. Amazing. So my next question, Microsoft, so they published an article, or I guess it was a blog post I was reading, and they mentioned that this chip is the, quote, transistor of the quantum age. Can you unpack that analogy?
Yeah, sure. So here's the analogy, right? Like, and I vehemently disagree with that statement. But spiritually, I agree that that's the aspiration that they would like to have for it. So let's take a look at the transistor, right? The transistor actually, of course, wasn't the first type of computer. There have been computers going around for quite some time, going back to the early electromechanical computers of the 1940s. But before that, there was a relatively successful technology known as vacuum tubes that were used in like UNIVAC and things like this beforehand. Vacuum tubes were actually quite different from transistors in a major way. They were far less reliable. In fact, actually, one of the things that's kind of fun is that with early vacuum tube technologies, this is where we get the term bugs from and debugging, because of, bugs literally going inside and getting zapped by the vacuum tubes and dying and causing problems inside the devices.
Yeah.
So these vacuum tube technologies, they could compute, but they were never really reliable. And, it would sometimes require a fair amount of effort and a fair amount of patience to deal with the unreliability of those devices. But they could still nonetheless do calculations that would have been impossible for just about any other platform at the time. When a transistor came around, we had our first taste of truly reliable computing, with error rates, well, not quite as good as what we can do with the best transistors right now, error rates that were negligibly small for the first time. Microsoft's technology promises potentially to end up one day leading to that sort of performance. But as I said before, the catch is that logically it has exactly all of the same pros and cons of the surface code based approach. The main difference is that it's likely, if we ended up carrying that out, we'd be starting at such a low level of error that potentially we might not need much in the way of error correction at all to lead to the kinds of reliabilities that we've been spoiled with on existing devices. So that's what Microsoft is aiming for. Now, what they actually have right now at the moment, that's the thing that I somewhat take a little bit of umbrage with, is that this device isn't clearly something as shown the level of errors that's consistent with a transistor scale device. But it's a vindication of their strategy that may one day yield a device which is kind of, what would be to existing superconducting quantum bits that companies like Google and IBM use. It would be to that like the transistor was to the vacuum tube.
I see. So are you saying like their vision is like this technology, this hardware will be so superior that it'll change the landscape of competition, and like all the other companies will eventually have to like adapt and like basically refine their strategy based on this type of hardware?
If Microsoft lands their strategy, that may very well end up being true. But, and I emphasize may, the reason why is, I said, all of the strengths and all of the weaknesses logically of their approach are shared with Google's approach to quantum computing at the moment. And so what that ends up meaning is if we end up getting into a world where the engineering problems of Google's much noisier qubits are so small compared to Microsoft's, maybe Microsoft does end up coming ahead. But for engineering reasons, it might just be far cheaper to end up building a ton of Google's crappier qubits and then relying on software error correction in order to emulate these more perfect quantum bits that Microsoft aims to build physically. We don't know at the moment which of these two approaches were coming in, but what I can say is it was looking kind of scary for the the topological approach until Microsoft's announcement, because the Google-ish approach with ordinary superconducting qubits had been moving ahead in a clear and sustained fashion. But progress seemed to have stalled on Microsoft's side, and this changes things. So at the moment, I don't think anybody really knows what direction we're going to be going in. If Microsoft stuff ends up coming up far ahead and ends up landing, the kinds of levels of error that we all hope that they'll be able to land within, the next few years, then that will probably, you're right, force everybody to reconsider their current strategy. If it takes another decade, though, for Microsoft to be able to land that chip, and Google already has working prototypes of a full air-protected quantum computer at that stage, well, then that's another question. It may not actually, even if it, at a technical level, is a superior technology, it may not actually be the winning technology. It may turn out to be sort of the Betamax of the quantum computing era. As in technically superior, but not capable of winning out due to market forces and established technology.
And I think this ties very nicely to my other question. So I have a question about algorithms, and I'm wondering how many of these algorithms that are in use are like truly hardware agnostic. Because if we end up like with one superior technology, like, do they have to like rewrite their algorithms for this new hardware, or like do they become obsolete, or like how does it work?
For almost all of the algorithms that we're looking at, the algorithms themselves do not have to change. This is something that we, if you think about what it means to build a quantum computer. A quantum computer is very much like a Turing machine in this sense, in that what it can do is anything that's a quantum computer can simulate in polynomial time any other model of quantum computing. So this means that if I have an algorithm that's written for one type of quantum computer, I can always translate it over. Now, there may be different costs depending on what you assume are the sets of operations that you end up having on it. Like, for example, I could write code for an x86 processor, or I could write code for an ARM processor. Fundamentally, they won't run on each other, and some may actually run slightly better than it would on the other due to the presence or absence of given instructions for one processor versus the other one. But fundamentally, they can all be transferred over. So that's not really necessarily an issue. But there are different opportunities, though, that are raised. If we want to be able to squeeze every last cent of performance that we can end up getting out of this, then it actually helps us to understand the realities of the hardware, the realities of the error correction schemes that are used on top of it, and build our algorithms and applications around this. So, to put it in perspective, right, one of the big advantages that ended up changing my childhood was John Carmack realizing his trick for doing the reciprocal square root quickly on x86 processors. This is something that allowed early first-person shooters to actually be done on the crappy processors that existed in the era, and that took advantage of low-level hacks that were specific to the floating point specification that was used. Similarly, we're going to be doing the same sort of things because our first generation of quantum computers are not going to be like our modern computers. We're going to have to push them as hard as we possibly can. And we're going to need some very dirty hacks like what Carmack ended up doing to squeeze the most out of it. So while the algorithms are likely to take the same basic form, their implementation and their optimization are going to require people that understand every aspect of the stack. So that way we can end up actually getting our code to end up running effectively on all sorts of different computers. That said, though, of course, there are some forms of quantum computing that are so different that it may suggest that we radically rethink the structure of some of our algorithms. For example, some of the more exotic types of topological quantum computing do require a rethink of what gates are expensive and what gates are cheap. But by and large, these are all more optimizations that are on the table, rather than something that requires some fundamental rethinking of how we would do Shor's algorithm for factoring or quantum simulation or QML.
Great. Let's keep talking about this chip. So my next question, we know that topological qubits promise stability, but stability is a relative term. How do we know that we're not just kicking the error correction problem down the road and trading one type of noise for another that we don't yet fully understand?
Oh, dude, we are going to be. It's totally kicking the can down the road. So to put it in perspective right now, right? I'd be very happy with topological qubits if we can get 10 to the minus 6 error rates, or 10 to the minus 10. To put it in perspective, 10 to the minus. If you're taking a look at the total number of gates that we need for an application, if we're looking at chemistry, I could change the world with some of the chemistry algorithms myself and my collaborators have developed, carrying out about 1 billion gates. So that means that we kind of, roughly speaking, need an error rate of about 1 in 1 billion to make sure that we can get through the entire thing without an error happening. So the point is that if we're already at 10 to the minus 6, then we don't really need that much in the way of additional error correction on top of that in order to be able to push it down. So that's the real hope, is that by starting out super awesome, you might not need a very sophisticated error correcting code in the end in order to push you the last little bit over. But this raises another question, and I'm really glad you brought this up, because not everybody recognizes this. The problem is, if we end up having incredibly small error rates, well, how do we identify what those errors really look like? If you've got an error rate of 1 in 1 billion, then you've got to repeat a calculation 1 billion times before you're going to end up seeing that error, let alone characterizing it. So the amount of data that we end up needing to get from our quantum computer in order to diagnose what many of these small errors are is brutal. At present, with the relatively coarse errors at about, like 1% to 0.5%, we don't need a ton of data in order to be able to identify what these errors look like and optimize our systems. But if we've got error rates that are that small, we won't necessarily know. And from that perspective, how do we know that quantum error correction has in fact actually reduced those errors that are hard to observe to something that's truly tiny? This act of verifying and validating our quantum computations, especially in cases where we can't check the answer afterwards, this is an interesting and open question, and I think a lot of people don't recognize the difficulty of how we would validate that our error correcting codes at this level are actually working as well as we think.
And so very quick, you mentioned you need 1 billion gates, and we know that all the companies are aiming for like 1 million qubit. What is the relationship between number of qubits and gates?
Well, at some level, with ordinary computing, there wouldn't be a relationship between the number of operations you carry out and the amount of memory you have. So, for example, I could end up running a really tiny program forever, and it might not need much memory, but it could take a lot of gates, i.e. operations, in order to execute. And on a quantum computer, you might say, well, I'd imagine the same thing would be true, right? That these two concepts are totally separate. But one of the problems that we end up running into is with our existing approaches to error correction, and this actually is true physically even for Microsoft's hardware, is that not all of our gate operations can be natively corrected. So what we do in order to be able to get around this inability to natively correct errors is a process is used called magic state distillation, where what we do is for the gates that we can't do in an error-protected way, we build copies of these quantum states that we can then consume in order to simulate a perfect operation of that individual gate. So it's a hack that we use to get around some of the loopholes in the theorem that says it's not possible. And the catch is that the more gates that we need to carry out, the larger and larger factories that we need in order to be able to produce copies of these quantum states on the fly to keep up with our simulation. And so that's one of the ways that ends up coming in. The next way that this ends up coming in is that the more gates that you end up having, well, the more smaller your errors need to be, which means the larger error correcting codes you need to compensate for the greater probability of error. So these two facts end up coming together in order to be able to make it so that actually the longer calculation you end up doing, the more memory or more qubits that you're going to need physically for it. And if you're taking a look at large-scale simulations, or if you're taking a look at problems like factoring large numbers, like a 2048-bit number for RSA, then the numbers actually work out to be shockingly kind of about the same. It usually works out to be about 1 million qubits. But if Microsoft ends up winning out, those numbers with their stuff, those numbers could go down dramatically to the point where you might only end up needing maybe 10,000-ish qubits rather than 1 million.
Great. How are we doing on time? Okay, great. We can ask many more questions. Yeah, so one of your expertise is quantum simulations, and I would love to know about quantum machine learning. So what does quantum computing bring to the table when it comes to machine learning that our like classical machine learning cannot do?
This is actually a big open question that ends up coming in, and was actually something that ended up confusing a lot of the people in the early days of quantum machine learning. So something that you'll hear people tell you is that the power that quantum computing ends up giving you comes from the fact that, with n bits, it can end up describing a vector of dimension 2 to the n. So the quantum distribution that you're looking at is dimension 2 to the n. And so this means that because of the fact that machine learning tasks often boil down to the manipulation of large vectors, it raises the intuition, well, why don't we just actually take those large vectors that we'd be manipulating in a machine learning problem and translate them over to a quantum state vector? If that were true, I could represent the same thing with exponentially fewer bits. And so then people ended up going through this and believed at first that actually they discovered algorithms that were exponentially faster than existing classical methods for machine learning. The problem is that actually the probability distributions, if you look at the dimension of a probability distribution on n bits, it's also exponentially big. And so it turned out that, and this is something that you and Tang did a great job of elucidating, but folks like myself as well as others have also looked at, is the fact that randomized algorithms can sometimes actually come close to tying the performance of some of these quantum algorithms for machine learning problems. So it's one of the problems, is that these huge speedups that we would hope for it often translate into much more modest speedups, i.e. polynomial rather than exponential speedups for machine learning tasks. And given the extra costs of building a quantum computer, as in, we're spending billions of dollars every year to build tiny ones, versus, you can go out right now and buy yourself, a NVIDIA card that is vastly more performant than any quantum computer that we, for ML tasks that we can picture at the moment. So the question really that we're kind of struggling with ML is, all right, well, what are the advantages for this? And I'm personally of the opinion that it's actually, I think it's unlikely that we're going to see massive advantages for existing ML tasks. I don't think that we're going to have a quantum analog of ChatGPT coming in. But the reason why I'm interested in quantum machine learning isn't for that. I'd like to understand what learning even means in a quantum world.
Mm-hmm.
I'd like to understand, if you feed an agent raw copies of quantum states that are drawn from experiments, or essentially given copies of molecules, what can you learn directly from those quantum states of matter? So I'm interested really in this question of fundamental quantum learning, where there isn't actually any existing classical analog for this. Because not only does it open up the range of problems that we can do with machine learning, it actually causes us to think more deeply about what learning even means and what the ultimate limitations and opportunities on learning are within the universe.
I would love to have a follow-up episode on this with a philosophy professor. But so OpenAI, they recently launched their new model, GPT 4.5, I think, and it was kind of like, it seems like we're kind of like plateauing in terms of like the capability of these models. So do you think the path to AGI and singularity is a fundamental like perspective shift, like inserting quantum machine learning into this problem, like a solution, or like more GPU, more data, like is enough to get us there?
I don't really know. I'll be honest with you. If you take a look at what the current approaches end up doing, right? Essentially what they are for LLMs is they're just giant token prediction systems where you end up giving a sequence of tokens that are coming in and you try to get it to predict the next sequence of them. There's kind of no fundamental understanding about what's going on, at least with the vanilla ones. They're building in on top of that with some of the additional reasoning models that have been put in. But at some level, it's kind of mostly just that. And it turns out that if you feed that, the sum total of human knowledge plus Reddit, yes, that was a dig at Reddit, and then you can actually end up getting a system that's that dumb, performing sometimes shockingly at a level that appears at first glance to be close to what humans are doing. I don't know whether or not we actually need a system that thinks like a human to be able to provide advantages for a human. In some ways, actually, having a system that doesn't think like a human can be a big advantage for a human because, well, I don't need somebody who thinks exactly like me to help me out. I need somebody who thinks at least a little bit different from me in order to do it. And similarly, it may be true that more data, larger models, actually is what we need, despite all the issues of reliability of new data on the internet right now and a whole bunch of other issues. But I guess the question to ask ourselves is, why would we hope that quantum machine learning would be the thing? I think a lot of people who end up taking a look at this are kind of influenced by Penrose and some of these other people who would like to believe that, the brain is mysterious and quantum is mysterious. So therefore, the two have to have something in common because all mysteries must have the same root, right?
Yeah.
But I don't buy that. I think that I'm not sure that there's any reason why we would fundamentally need something like quantum mechanical effects in order to be able to have valuable machine learning solutions. In fact, actually, I'm more of the opinion that machine learning, at least as we currently see it, might have more value for quantum computing than quantum computing will have for machine learning. Because it will potentially give us ways of designing better decoders, for example, for our quantum error correcting codes, or better ways to diagnose what's going wrong with one of our noisy quantum devices that we have in the early era, rather than us using quantum effects to be able to do this. So, as I said before, to me, I really feel that the right thing to do for this, for looking for AGI, I think you're probably better off talking to a true ML expert for this, but I really wouldn't be surprised if what we ultimately end up needing to do is taking existing LLMs as just being part of the solution and tacking on families of different types of models on top of it. And through an appropriate collaboration of a diverse set of models, we might be able to get something that is like AGI. But on the other hand, I'm not sure we actually even need AGI. After all, humans are pretty good GIs. We really need something that's capable of augmenting humans. Mm-hmm. And there may be other things that aren't really generally intelligent that may serve that purpose far better than trying to mimic the very thing we do best.
Mm-hmm. Yeah, that's very interesting. I'm very interested in knowing about the type of problems that you're trying to solve with quantum machine learning and quantum algorithms. So if you had the quantum computer that you need to solve these problems, what would be the first problems that you would aim to solve?
Okay. So if I was looking at quantum ML in particular, one of the things that I am kind of most interested in this is that if we take a look at chemistry simulation, the fundamental problem of chemistry simulation, at least as we commonly think about it, is to prepare the minimum energy configuration of a molecule and answer questions about its properties. But the thing that ends up happening is that if we take a look at two similar molecules, they're often going to have similar properties for their ground states. And so if we try to solve a new problem, and we've already solved a bunch of other ones, we're kind of, with present approaches, not using any of our knowledge that we have from previous examples that we've seen. Mm. So first thing that I would like to do with quantum machine learning is do something like the following. What I'd like to be able to do is train it with a ton of different, a model with a ton of different simulations of different molecules that a quantum computer can generate like crazy because it's exponentially faster for doing this, at least with high precision, than existing computers. So you generate a ton of high accuracy solutions, and then you build a model for approximating the solution for all sorts of molecules you haven't seen. Mm-hmm. Now, what you will have is you'll have a situation where you won't have to repeat those incredibly expensive quantum calculations. You can now use a quantum AI to be able to simulate the outcomes of all of these experiments that you've never done before. Mm-hmm. Those are the sorts of tasks that I would like to do. I'd also like to do things like the following. Imagine that I have a material that I'm trying to simulate. I'd like to understand what the properties are of this material, or I'd like to be able to understand some features of them that might make some families of materials superconduct and another family not superconduct. Well, so what I would do is I would say, okay, let's load this into a quantum computer. Quantum computers can generate the training data. They'll generate a bunch of states that have these different properties. I can feed them then into a quantum ML algorithm and learn a good quantum function that will be capable of deciding and selecting a promising material candidate before I even try, and potentially even predict literally what its properties are going to be before we start. Those are the kinds of tasks that I think could end up having value. And you'll note in all of those cases, the raw data that's being fed in or the prediction that's coming back out is always going to be quantum mechanical, rather than something that I could address with, say, existing deep learning techniques.
Great. Well, that was amazing, and I think I learned a lot. I would like to finish with a analogy-based question. So my background is in biology, so this is kind of like I guess a good analogy that I found. So single-cell organisms started as simple systems but scaled into complex multicellular life by coordinating interactions. Qubits today are fragile, error-prone, and need correction. Could quantum computing require a similar evolutionary jump where instead of isolated qubits, we engineer quantum organisms that self-correct, adapt, and scale naturally?
Well, that's a wonderful analogy. I've actually never heard that before. Perhaps, again, because of the fact that at present, there are far fewer people, who come from a biology background in my field than from a mathematics, computer science, and physics background. But to some extent, quantum error correcting codes end up actually fulfilling a similar sort of role. What we do in a quantum error correcting code is, as I was saying kind of before, we store the essential information that we're interested in, not in single qubits, which would be like the analog of your single-celled organisms, but rather we store it collectively in the information in the entire system. And just like a multicellular organism, I can scrape skin cells off my fingers all the time. And, tons of organisms, single cells in my body end up dying constantly. But nonetheless, the information that I believe is the essential information that constitutes me is kept alive inside my body through redundancy. We're trying to do the exact same thing in quantum. And, about the adaptive part of it is really just us identifying what goes wrong and trying to fix it one step at a time as it ends up happening. And this leads to kind of almost this evolution of the current quantum state to the individual error measurements that you've had inside there. So to some extent, yeah, it's perhaps a much better analogy than I had thought about what we're trying to do. The biggest difference, though, that we end up seeing is that if we are taking a look at the individual single-celled organisms, there's already a whole bunch of error correction that already is being used effectively in the DNA replication process itself. So from that perspective, I guess what I would say is maybe your analogy would be closer to what Microsoft is trying to do. To have, some redundancy in the individual cells, like Microsoft is trying to do with their topological qubits, and then putting that together to build a larger multicellular organism, which would be the quantum error correcting code they're building on top of their single-celled organisms.
Great. Yeah, I mean, Microsoft also has this project. They're trying to build a biological computer. Yeah, I think that's cool too. Wonderful.
Hey, DNA storage 10,000 years sounds pretty nice.
Yeah. Well, that's wonderful. Thank you so much. And so last question, life advice for young people.
Great. You know what? This is something that is difficult sometimes to give because young people are, of course, a very diverse group of people. And, I can't say my trajectory is likely to be similar to other people. For me, one of the things that happened, was that my experience was that I was never a very good student. So I was somebody with a low B average going through. It was a question about whether I would even get into grad school in the first place. Then, after going to graduate school, I had people constantly tell me that, I wasn't smart enough to be a theorist, but I just might be smart enough to be an experimentalist. Awful advice, by the way, in retrospect. I realized, much to my horror, that I was smart enough to be a theorist, but not smart enough to be an experimentalist. But the point is that along the way, what will end up happening is there's just going to be a ton of events like that you end up seeing in your life. People telling you that you're not good enough. You telling yourself that you're not good enough. Having bad referee reports coming back. Having setbacks in your career, in your research. One of the biggest things that I think ends up separating the great scientists versus people that die out in the field it isn't actually the frequency of these setbacks, but rather the way that they end up dealing with them. Building up a tolerance to setbacks and a tolerance to failure is one of the most important things in this, and learning that this is actually just part of the inevitable process of going through, and frustration along the way is actually a tool for growth. And learning and training yourself to get back on the horse and recognize frustrations for learning opportunities. That's the biggest advice that I could give. Unfortunately, it's hard advice to follow. And, but it's advice that can make the difference between, your career prospering and you suffering from burnout. So get used to failure. Learn to embrace it and learn to grow with it, because guess what? If you're going to be pushing yourself to the frontiers, failure is going to become one of your closest friends.
I hope you enjoyed this conversation as much as I did. If you liked this episode, please consider subscribing and maybe sharing it with someone who would find it interesting. Thanks for listening, and I'll see you on the next one.